and good morning to sir. It is indeed a great honor and pleasure to welcome you all for the distinguished lecture program organized today by IEEE Signal Processing Society Student Branch Chapter, IIT Kharagpur. On behalf of the student branch, I, Shovik Sinha, Vice Chair, would like to welcome the participants and our distinguished lecturer for today, Dr. Yu Lu. We are grateful to him for accepting our invitation as the distinguished lecturer for today's event. Kindly allow me to introduce our lecturer for today. Dr. Yulu attended the University of Illinois at Urbana-Champaign, where he received his MSc degree in mathematics and his PhD degree in electrical engineering, both in 2007. After his postdoctoral training at EPFL Switzerland, he joined Harvard University, where he is currently Gordon Mckay Professor of Electrical Engineering and Applied Mathematics at the John A.Paulson School of Engineering and Applied Sciences. He has also held visiting appointments at Duke University in 2016 and the ENS in 2019. His research interests include mathematical foundations of statistical signal processing and machine learning in high dimensions. Today, our guest is going to talk about exploring and exploiting high-dimensional phenomena in statistical learning and inference. He would discuss recent works on signal estimation and multilayer neural networks where such high-dimensional phenomena analysis are required. Now, I request all the participants to mute their mic, and we shall take up questions after the end of the session. So I now hand over the floor to Sir. Sir, over to you.
Okay, thank you very much, Suvik, for your introduction and also for the invitation. Can everyone hear me clearly?
We can hear you loud and clear, sir.
Great, thank you very much. It's a pleasure to speak at this seminar. Today I'm going to present some of our results on understanding signal processing and machine learning problems in high-dimensional settings. We're interested in this so-called high-dimensional setting because a lot of modern data sets are inherently high-dimensional in nature. So here I give a list of example applications from large-scale image processing to biomedical data analysis, from scientific experiments to the monitoring of distributed cyber-physical systems, such as the power grid. In all of these applications, very large quantity of data are being produced, and efficiently processing such data sets to extract information provides a lot of challenges as well as opportunities. Now, this talk is about high-dimensional data analysis, so it will be useful to formally define what we mean by high-dimensional data sets. For the purpose of this talk, we're going to assume that our data is going to be stored in the form of a matrix with d rows and n columns. Okay, so each column represents a sample from our data set. For example, if you think of an online image hosting service with 10 billion shared images, each image is going to be a column of this matrix. So we have a total of n equal to 10 to the power of 10 columns. And for simplicity, let's assume every image is of the same size, 10 megapixels. And then you also have RGB information. So D, the number of entries per image, is going to be 10 to the power of 8. So in a high-dimensional regime, we are going to assume that both N and D are large. Now, most of the challenges in processing high-dimensional data sets come from the so-called curse of dimensionality, and this is a term coined by Richard Bellman in his book on dynamic programming. It essentially says that a naive exhaustive enumeration or search in high-dimensional space is not going to be tractable because the complexity grows exponentially in the underlying dimension. And I'd also like to point out that in high-dimensional settings, there can also be many counterintuitive phenomena. In addition to challenges to computational complexity, there are strange phenomena if you are not already familiar with the high-dimensional setting. So I'm going to use a very simple example to illustrate this point. Suppose you are going to estimate a vector or direction, psi. Okay, you can imagine this psi is on a sphere, it's pointing towards the North Pole, right? And x is our estimate, okay? And you're going to measure the quality of this estimate by the angle theta between the target and our estimate. All right. Of course, the optimal case is theta equal to 0. You have perfect estimation. And the worst case is when theta is equal to 90 degrees. That corresponds to an estimate that is orthogonal to the target, right? Now, let's consider a very modest goal. The goal is to just have an estimate such that angle theta is less than 89 degrees, just a little bit better than orthogonal, okay? Now, in the low-dimensional setting, this looks like a very, very simple problem because you can just pick a point randomly from the sphere, and then with high probability, you're going to satisfy our requirements, right? Now, let's do this experiment, and then we can show that in this case, this is the probability of success of just getting a random estimate from the sphere, and what is the probability that the random estimate will have an angle less than 89 degrees. Now we can see that initially, the probability is indeed pretty high. It starts around 0.5 because have 50% chance you're going to get a point on the upper hemisphere, right? But as you increase the dimension, so the horizontal axis is about the dimension of the problem. So in the figure on the left, dn equal to 3, but we can consider general n-dimensional spheres. As you increase the dimension, you can see the probability of success goes to 0 very, very rapidly. Okay? So what's going on is that our geometric intuition in high dimensions are no longer reliable. So instead of thinking about a sphere as something on the illustrated by the picture on the left, a more accurate cartoon for a high-dimensional sphere is something on the right. Now, the green region, which corresponds to the 89-degree cone around the North Pole, is only occupying a tiny fraction of the sphere in high dimensions. The majority of sphere, the gray region, correspond to stuff around the equator, a very narrow band around the equator. Okay, so this is a more accurate illustration of what's going on in high-dimensional sphere case. And of course, if you have seen this before, you know that this is so-called concentration measure phenomena, which says that if you pick a point uniformly random from a high-dimensional sphere, then with high probability, that point is going to be concentrated around a very narrow band of width 1 over square root of n around the equator. So with high probability, the random guess that you get is going to be nearly orthogonal to your target. Okay, so you cannot do random guess in this case. All right. Now, instead of dwelling on these challenges or counterintuitive phenomena in high dimensions, the main message that I want to convey in this talk is that there are also many nice properties happening in high dimensional setting, and we can call these the so-called blessings of dimensionality. So here I list a few very important unique phenomena of blessings in high dimensions. The first one is so-called concentration phenomena, and the second one is the phase transition fundamental limits. The third one is the universality. I'm going to use simple examples to illustrate each of these blessing or unique phenomena. So I'm going to start with concentration. This is a very, very simple question. I always show this question to my students of introductory probability. Suppose you're going to toss a fair coin 1,000 times, and then you're going to count the number of heads that you see, okay? And what is the probability that the number of heads you see out of 1,000 tosses is greater than 600? Now, you know that this is going to be a fair coin. So on average, you're going to see 500 heads. But this is random, so you have to allow for some statistical fluctuation. Now, 600 represents 20% fluctuation around your expectation, right? Okay. So what is the probability of a 20% fluctuation? Is it lower than 1 over 10, 1 over 1,000, 1 over a million, or 1 over 10 billion? So everyone can already take a moment, do a mental calculation based on your intuition or gut feeling what the probability should be, the answer turned out to be D. It's a 1 over 10 billion. It's a very, very low probability. So in other words, we can see that in this case, a 1,000-dimensional problem, the chance that the random quantity deviates more than 20% from your expectation is exceedingly unlikely. So the probability is lower than 1 over 10 billion. And because of this, we get to study these random events by their deterministic limit. So this is, of course, the very well-known law of large numbers. If you look at the number of heads divided by n, then you know this is going to converge to the expectation, which is 1 over 2. And you can also get some more refined asymptotics. You say the number of fluctuation around this expectation with proper normalization is going to be a random variable whose probability distribution is going to be a Gaussian. This is central limit theorem, right? So in some sense, what I'm going to talk about next are nothing but more advanced versions of the law of large numbers central limit theorem in different settings, right? And by the way, you're also welcome to ask questions during the talk in case there's anything that is not clear or you want me to elaborate on certain points. Okay, we don't need to wait till the very end for questions. The second example that I'm going to use is to illustrate the so-called phase transitions. Now, imagine you have a figure on the left. This is a map of a big city, for example, the New York City. And you have city blocks, and the segments represent streets. Okay. Now, we can consider an experiment. We take a parameter c, for example, c equal to 0.3. Then you go through every single street with probability c. That street is going to be open, and you keep the street, you keep the line segment. With probability 0.7, 1 minus c, that street is going to be closed. So you're going to remove that line segment. So in the case of c equal to 0.3, if you do this experiment, then on average, 30% of the streets are going to be open, 70% are going to be closed. If you increase c, then you're going to get a denser type of open street network, right? Now, imagine you live, your house is here in the center, and you want to ask the following question. Starting from your house, what is the chance or what is the probability that you can find a path from the middle that allow you to escape this city? So you can leave from your house and find a way to get out of the city. Okay, so you can see in this case of in the case in the middle, you cannot find a path that allows you to leave the city. But for c equal to 0.6, in this particular realization, you can indeed find a path that allows you to leave the city. So we want to find this probability that you can escape so-called the maze from the origin. And this, of course, the probability is going to be a function of c, a non-decreasing function of c. Now, you might wonder why we want to study this problem, or what are the applications of this. This is, of course, known as a percolation problem. It serves as a model for problems in material science. You can imagine there are liquids, and you want to understand under what conditions liquids can go from one side to the other. There are also applications in epidemiology. In this case, you can imagine this this network is a network, a social network, okay, a contact network with human, and then a link present means that it's possible to infect certain people, because if there are a link between the two persons, if the link is absent, means it's not possible to infect. And then you want to know what is the probability that a single infected person can burn through this entire population if you have a different type of connectivity structure. Okay. All right. So the problem is finding PC, and this problem has been computed for the case of a two-dimensional grid. The answer turned out to be this function. Now, what I want to point you to is the feature of this function, P of C. You can see that P of C initially is equal to 0 when C, the parameter, is lower than a value C star. And this is a phase transition. So before C star, there's no chance for you to escape the maze. But once C is greater than C star, then the probability starts to become non-zero and gradually increase to 1. Okay. Now, in a classical paper by Keston, he shows that the critical value is 1/2. Okay, so in this problem, 1/2 is essentially the fundamental limit. If you want to be able to escape the maze, then you better set C to be greater than 1/2. Or in other setting, if you don't want, for example, a disease to burn through this entire population, then you want to make sure C is lower than C star. And this is a phase transition phenomenon. Okay. Now, next, I'm going to use another example to illustrate what I mean by universality. Again, we can think about a very simple experiment. Suppose you're going to construct an n by n matrix. Now, this matrix is going to be populated by random entries. What I mean is you go through each entry of this matrix, and then for each entry, you're going to generate an independent random variable and put that random variable in the IJS entry of this matrix. And you go through all the entries. You have a total of n squared entries, and you generate a random matrix in this way. Okay. This is something that we can very easily do on your computer. Now, this matrix is not symmetric. So if we calculate the eigenvalues of this matrix, the eigenvalues are in generally complex values, right? So you have to, if I'm going to plot the eigenvalues, these eigenvalues will be living on the two-dimensional complex plane. So let's just do this experiment. Let's populate entries A by, for example, ID Gaussian random variables or ID Bernoulli plus minus 1 random variables, and plot eigenvalues. And this is what you would get. You can see the eigenvalues are going to be uniformly distributed within the unit circle. Okay, this is a very classical result in random matrix theory. Now, and it's also known as the circular law. Now, what is interesting is the following fact. Although the exact location of each eigenvalues is going to be random because the matrix is random, but if you look at the density of these eigenvalues, the density has nothing random, so they are always going to be uniformly distributed over the sphere. And also, it does not depend on how you construct the matrix. You can populate A by Gaussian random variables. You can populate A by discrete random variables. You only need to make sure that these random variables has zero mean and univariance. Okay, so this is a so-called universality phenomena. It does not really matter what the microscopic construction of the system is. If you look at the macroscopic property, in this case, the density of eigenvalues, they are going to be universal. All right, but there's even more to the story. We don't even need the entries of A to be random. So let's just fill A. Suppose A is a 2000 by 2000 matrix, so you have 4 million entries. Let's just fill the 4 million entries of A by the first 4 million digits of pi, okay, which is totally deterministic sequence, right? And this is what we will get. You can see the result looks the same. So this is a very strong sense of universality. We don't even need randomness. So if you look at the spectrum, the density of eigenvalues with very limited conditions satisfied, all these eigenvalues are going to be uniformly distributed within the unit circle. All right. Of course, this is a very general phenomena. Many large systems, complex systems have been observed to have universality phenomena. Now, I want to argue that this is going to be a blessing and we can exploit this blessing of universality using this picture. So suppose you are going to study a system A, or whatever system, right? But it is somehow difficult to analyze. Maybe we don't have the mathematical tool to analyze system A. But if you can show that A is in the same universality class of other systems, such as B and C, then you can study system B, if it is easier to work with understanding that whatever properties that you can derive out of system B can be transferred to system A due to universality. Okay, this is something that we are going to exploit in the later part of this talk. So in this talk, I'm going to focus on two concrete problems. One is a spectral method. The other one is about learning with random features. Let's start with the first problem. In case there's any question, feel free to pose a question. I cannot monitor the chat. You can you can post your question in the chat box, or unmute yourself and ask questions right away. All right. So
there are no
yes.
questions so far.
Okay. Yeah. Sure. All right. So I'm going to start with the first part. Spectral method for non-convex statistical estimation. Or I'm going to start with a concrete problem. This is a problem of phase retrieval, and people in signal processing, image processing have been working on this. So it doesn't matter if you have not heard about phase retrieval. Mathematically, this is a very, very simple formulation. The formulation is the following. You want to estimate a vector Kasai. This is the vector that you want to estimate. And in applications, Kasai is actually representing an image that you want to reconstruct. Okay. Now, what you can observe is Kasai going through a linear system. So A is some sort of a system matrix. Okay. And then what you can get is A times Kasai. All right. But in phase retrieval, instead of getting A times Kasai, okay, this vector, what you get is A times Kasai squared. Okay, so for example, if you have entry -3 in A times Kasai, what you observe is 9. So effectively, what you are missing is a ±1 sign information, or in the case of a complex valued vectors, you are missing the phase information, right? Because if you know the phase, or if you know A times Kasai, then estimating Kasai is just nothing but a linear inverse, right? But if you don't know the phase, then you have to first estimate the phase before you do the linear inversion. And this is why the problem is called phase retrieval. And there are a lot of applications in X-ray crystallography, imaging, communication problems, and so on. Okay. Now, if you want to solve the phase retrieval problem, a general formulation is just you want to solve a minimization problem where the cost function has two parts. The first one is the loss function that measures how good a match your postulated solution X is to your observation, and the other one is some regularization term. But in the case of phase retrieval, if you write out the loss function, you can see that typically the loss function is not convex. So you're not dealing with a convex optimization problem. So if you have worked on optimization, you always like convex problem because then things are nice and easy. But if you have non-convex problems, this is potentially the case that you have to deal with. In addition to the global minima, you also have a very large number of local minima, and in practice, algorithms can be easily stuck in one of the local minima before you reach the global minima, right? Now, for non-convex optimization, recently there is been a very popular strategy, so-called two-stage approach. What you do is in stage one, you first find, suppose you want to find psi, which is in the global minima. You first try to find a good initial guess x of 0 that is hopefully within the basin of attraction of the global minima. And then once you can find such an initial guess, then you can, of course, do local refinement, for example, gradient descent, to try to find psi. So critically, you need to be able to find a good initial guess. So I'm going to show you a very simple algorithm for finding an initial guess that can be typically fairly good. Now, again, this is our model. Here, the subscript I indexes the number of measurements. So you have total of m measurements, and I is the ith measurement, starting from 1. The ith measurement, y of I, is equal to the inner product between the vector you want to reconstruct, Psi, and AI, the ith row of the matrix, absolute value squared. Okay, this is a model. From AI and yi, you want to estimate Psi, right? Now, the algorithm that we're going to use is very simple. It only has 2 steps. The first step, you want to build a matrix D as a weighted linear combination of AI and AI transpose. The AI, again, is the row, the ith row of the matrix. Okay, so this is going AI transpose rank 1 matrix, weighted by the corresponding measurement yi. Okay, you get the matrix D. The second step, you find the top eigenvector D. Okay, this is just going to be your initial estimate, and this is literally a 1-line MATLAB code. If you want to simulate this algorithm, 1 line. Okay, you get your x1. All right. But why does it work? Why does this algorithm work? If you think about the case of random design, meaning that if the sensing vectors are assumed to be drawn from some Gaussian distribution, if you look at the data matrix, okay, so it's written in the form of an average of yi, ai transpose, and for different i's, things are independent. So D is nothing but an empirical average of independent, identically distributed random quantities. Then you can use some sort of law of large number to say that D should be close to the expectation of D. And if you calculate expectation of D, you will see that expectation of D for this model is exactly equal to identity plus 2 times Kasai, the target signal, and Kasai transpose. If you calculate the leading eigenvalue or eigenvector of this expectation matrix, you will see it is exactly equal to Kasai. All right. So of course, this is an old idea. It has been proposed in the statistical literature under the name of principle Hessian direction and so on. Okay. But although this algorithm is very simple, it's not a trivial task to analyze the performance of this method precisely. And the way we measure the performance is just to look at the angle. This is exactly what I showed at the beginning of the talk. Kasai is a target, and x1 is your estimate, and we're going to measure the quality by the angle, or equivalently, you want to measure it by the cosine of the angle. So the cosine is nothing but normalized inner product, right? Okay. And what we want is to understand under what conditions we can make sure that the angle is small with high probability. And there's been a serious work in the literature, initially in the paper by Natropoli and his co-authors. They showed that you can satisfy this requirement as long as the number of measurements, m, is large enough. And precisely speaking, m needs to be greater than a constant times n, the dimension of the problem, times some additional log factor, log n to the power 3. And this result was later improved by dropping log n to the power 3 to log of n. And later, the log factor has been dropped. What people have shown in this paper is that m just needs to be larger than a sufficiently larger constant C3 times n. Okay, but the C1, C2, and C3 are just some unspecified numerical constant. Now, if you actually do the experiment, remember the one-line MATLAB code, you can see that in this case, the performance, cosine of the angle between Kasai and x, has this phase transition phenomena. Here, the horizontal axis is the number of measurements per dimension, m over n. N is the number of dimensions. As you increase this ratio, then the correlation is indeed going to be close to 1. In some sense, what people have shown are the results up here when alpha, m over n, is very large. But what we have missed is this region where alpha is not that large. You can see in particular there is a phase transition phenomena around, in this case, 1.8. Before this value, the correlation is 0. After this value, the correlation starts to become non-zero. And this is, of course, a critical threshold, which is fairly important in practice. Practitioners need to know what is this threshold so that you know that you have to take more measurements than what this critical threshold indicates. So this is indeed something that we can analyze by using the blessing dimensionality, the concentration, and so on. What we have shown in this work, it shows that if you have Gaussian sensing vectors, and if the dimensions are large, then the angle between the target vector and your estimate obtained by the eigenvector is going to converge into deterministic quantities that has this phase transition phenomenon, depending on if alpha, the ratio, is less than or greater than this critical threshold alpha c. Okay, and here I simplify the formula. In the paper, we have exact expressions for computing alpha c and theta star of alpha. Now, geometrically, so here, first of all, some simulation results. You can see that we have this image, and then we do experiments, and then the stars are the simulation results, and blue and red lines are what the theory can predict. You can see that in this case, the theory predicts the actual performance very well. And the error bars are also very, the range of error bars are very, very small because they always concentrate very tightly around the theoretical prediction, right? So geometrically, the result shows two different phases. If alpha is less than alpha c, meaning that you don't have enough measurement, then the theory says that the angle between the target and your estimate is going to converge to 90 degrees. 90 degree means that your estimate is going to be living around the equator, being orthogonal to the true signal. This is uninformative estimation. You don't have any information whatsoever. But once you have alpha greater than alpha c, then the angle is going to be converging to something that is not equal to 90 degree. So you start to pick up some correlation. All right. Okay, so once you have this theoretical prediction, you can also start to do optimization, because we don't need to use yi, the measurement, to form the matrix. We can also first do some pre-processing. So we first apply a function t to yi before forming the matrix. And in the literature, there have been all kinds of proposals of how you would change t based on different type of heuristics, intuition, and so on. So the problem boils down to finding the optimal function t so that the performance of this method is optimized. So I want to skip a little bit of detail, but here, by using our asymptotic characterization, we can find that this is the optimal form of the function that you should use. There's no need to have any heuristic or intuitive guess. This is going to be the function that we should use. In the concrete case, suppose the model is a noisy type of imaging problem where you have Poisson noise. Using our formula, the optimal pre-processing function is of this form. Okay, so the point I want to show is this form is not something you can guess by intuition or by heuristic. You have to know exactly what you're doing to know this is the optimal function that you should apply. And here are some simulation results. Now, the horizontal axis, again, the number of measurement per dimension. The vertical axis is the correlation. The higher, the better. The red line is what you would get if you use some sort of a intuitive guess for the function t. But the blue line is what you would guess if you use optimal function. You can see that by using the optimal function, then the performance, meaning the correlation, is much, much higher at the same, if you take the same number of measurements. Okay, all right. Okay, so before I move to the second topic, I want to say something beyond the Gaussian design, so towards more physically realistic models. So far, in the results that I've shown you, we have assumed that the sensing matrix A has ID Gaussian entries. Okay, this model is very convenient for deriving theoretical results, but they are very far from reality, because if you do an actual imaging setup, the sensing matrix A arises from the physical model of your imaging system, and there's no reason that A should have independent Gaussian entries, and there's actually no reason why A should be random at all, right? And here is a more realistic type of model, so-called coded diffraction pattern. I want to skip the detail, but mathematically, if you look at this more realistic imaging setup, it corresponds to this type of sensing matrix A, which has a block structure. So it has different blocks, in this case, K blocks. Each block, for example, the first block, is written as F, the DFT matrix. You can think about a Fourier transform times lambda 1. Lambda 1 is a diagonal matrix of random plus minus 1 plus minus I entries. Okay, and the second block is the same DFT matrix times a different random diagonal matrix. So in this case, this A is still random, but the amount of randomness is much lower than ID Gaussian, because you only have random diagonal in this case, and majority part of this matrix is deterministic, given by the Fourier transform, right? So if we want to do the simulation, you can see that in this case, the yellow line is what the Gaussian theory can give us, and the blue stars are what the simulation results will give us if you have sensing matrix with Gaussian entries. But the problem is, if we consider this more physically realistic model, the simulation results give us these red circles. The red circles are what you would get if you have these more realistic sensing matrices. You can clearly see that the Gaussian theory cannot predict the actual performance of this so-called CDP type of model. Where's hope? The hope is universality. Okay, so you can, if you look at, you can do this experiment where again the circles correspond to the coded diffraction pattern, the systems that we want to analyze. But we can also consider some additional ensembles or sensing matrix, in particular the unitary matrix, which is start from a Gaussian, but you orthogonalize the Gaussian matrix. Okay, you do an SVD on the Gaussian, and then you pick the random singular vectors. You can see that the unitary ensemble have the same performance of the CDP. So they are universal. So if you use the unitary ensemble to analyze the problem, because they live in the same universality class, but unitary ensemble is still fairly close to Gaussian. We have a lot of properties that we can exploit. You can obtain the exact analytical curve of this result, and the blue line is what you will get by analyzing the unitary ensemble. Okay, this is something that we can still handle, but you can see that the unitary ensemble, the theory, the blue line, can also accurately predict the performance of the CDP, which is the actual system that we want to analyze. And this is a concrete instance where we have explored universality phenomena in this problem. All right. Okay. I want to move on to the next part, but in case there's any question, feel free to ask. This is a good point for pausing the talk for a few moments in case there's any question. If there's no question, I'm going to move on to the second part. It's about learning with random features. It's about some theoretical models of machine learning. First of all, I'm going to very quickly remind you of this basic setup of supervised learning. In supervised learning, what we are given is a collection of training samples, xi and yi. You have a total of n training samples, and you can think about xi as images. For example, a collection of images of cats and dogs. Yi's are the labels. So cat images are assigned label 0, dog images are assigned label 1. Okay, and given these training samples, I want to learn an algorithm so that when I'm given a new image, I should be able to correctly, with high probability, predict the actual label, is that cat or dog. Okay. Now, a simple case is when these training samples are linearly separable. So because xi's are nothing but high-dimensional vectors, you can plot these in a high-dimensional space. And the red dots correspond to the first class, green dots correspond to the second class. If they are linearly separable, then learning a classifier corresponds to learning a separating hyperplane, right? There are many possible hyperplanes, and each plane can be encoded by its normal direction. And then you can find a separating hyperplane by solving an optimization problem. This is so-called empirical risk minimization. And W here is the weight, or you can think about as a normal direction of this hyperplane. Okay, and L here is the loss function, and R is a regularizer. Okay, this is a classical setup. But the challenge in practice is that the actual data that you're dealing with, images of cat and dog, they're not linearly separable easily. A more realistic situation is when these two classes can be separated, but not by a hyperplane, but by a surface. Okay, but a surface is much more challenging to describe. So a natural idea is to do a feature map. What you do is you apply a transformation T to your images and hopefully lift the images to a high-dimensional space. Okay, and with the idea is that in the feature space, the transformed data points can indeed be linearly separable. Okay, so this is a feature map, and a very popular way of implementing a feature map these days is to use a neural network. So here, this is just a very simple two-layer neural network. You have the input data. It goes through a linear transformation encoded by matrix F. And then you have entry-wise linear transformation. And afterwards, at this point, you have the features. And then you apply a linear classifier at the last layer. All right. Now, in this case, if you want to do training, meaning finding the optimal separating hyperplane and finding the optimal feature map, you're still solving a minimization problem. But in this case, in addition to finding the last layer weights, you also need to find the matrix in the middle at the first layer, right? You want to also optimize the weights of this matrix, right? But of course, this is much more challenging because you have to optimize two parts. Now we're going to study in this work a middle ground. So instead of optimizing W and F simultaneously, we're going to assume F, the first layer weights, are given and frozen. Okay, so this is so-called the random feature model proposed in this paper by Rahimi and Rett, and also it appeared in other settings under the name of extreme learning machines. Now we are going to assume that F, the first layer weight matrix, is drawn from some random distribution, but then it's frozen. You're still going to, so in this case, this is a random feature map. You're going to find the separating hyperplane W at the last layer, right? Okay. And in this case, the optimization problem is simpler. You only need to optimize over W, okay, by solving this problem. All right. And typically, this problem loss function is very simple. For example, logistic loss, and R is, for example, quadratic function. Okay. Now, I'm a theoretician, so I want to analyze the problem precisely in a high-dimensional setting. So, what are the quantities that you care about? The first quantities that you care about is the training loss, meaning that if you are given a set of training samples, what is the result of this optimization? And typically, training loss, the lower the better. You want to know what is the training loss. And also, the second quantity you want to find out is the test error, meaning that once you have learned this neural network and you are given a new image that you have not seen in your training, what is the prediction performance of your learned neural network? This is so-called the test error, right? Okay. And we can also typically, in theoretical analysis, we can make some statistical assumptions on how the data are generated, and so on and so forth. And I want to say that there's this one special case where the analysis is very simple. The special case is when sigma is a linear function. So let me just remind you what sigma is, because I don't expect everyone to have noticed what sigma is. Sigma is the linear transformation you apply in the neural network. For example, ReLU or Tanh, right? But if sigma is linear function, sigma x of e equal to x, then the feature vector is just f times xi. If you assume x of I are Gaussians, then the feature vectors are still going to be Gaussian vectors. And then if you have Gaussian vectors, and then there are a lot of mathematical tools available for you to analyze optimization problems in this form. So it doesn't matter if you have not seen this kind of thing before. The point I want to make is that it's a very nice playground for theorists, because you have, on one hand, you have a lot of problems. On the other hand, you also have a lot of available and mature, powerful tools that you can use. You can derive a lot of results. But the challenge here is that in this case, the feature vector is not Gaussian, because sigma can be a nonlinear transformation, right? So even if f times xi is a Gaussian vector, after a nonlinear transformation, you no longer have a Gaussian vector to begin with. So all these tools developed for Gaussian data are no longer applicable. Okay, so we're going to consider two versions of the feature map, and there is some very interesting, initially mysterious observations that people have made in the literature. So you can think about the first map is original feature map. You have a nonlinear transformation. The second one is a different feature map, if you compare A and B, you can see that there's no sigma, there's no nonlinearity. Okay, B is linear in f times x, but in addition to the linear term, you also need to add z. That's a new term, and z is just going to be an independent Gaussian noise. So in some sense, B is linear but noisy. You have additional noise, and you can calculate the training and testing error for A version and B version. And just let me remind you, A is a system that you want to estimate. B is some system that you created by yourself, right? And you also can calculate test error and for A and B. What people have observed is that in a high-dimensional case, the training and testing error of the two versions, A and B, are equal asymptotically. So if you do experiment, you can see that the two quantities are match exactly each other. Okay, so there's a series of papers that have observed and exploited this conjecture. Why is it nice? It is nice because if we get to work with B, then there's no nonlinearity. Then everything is Gaussian again. And we can have a lot of tools. So without going into the detail, I'm going to skip this technical slide. You can see that this experiment of learning with ReLU nonlinearity or tension nonlinearity, and here, if you look at the black crosses, these are. So let's start from the orange dots. The orange dots are the training and testing error of the original nonlinear feature model, okay, the system that you want to estimate. And the black crosses are the corresponding quantities of the noisy linear model. You can see they fall right on top of each other in this finite dimensional experiment. And also the noisy linear model, the linear Gaussian model, can be analyzed. And here the green line and the blue line are the theoretical curves that we can get. You can see that by doing this, we can precisely quantify the performance of this learning problem and deriving its testing error and the training error, right? And this is the figure on the right is about a different setting where we have a logistic loss. All right, but the question is, how do we prove conjecture? Or in principle, what is the reason why the A version and B version should be equivalent? Now, if you look at A and B, and here mu0, mu1, mu2 are just some scalar constants that you have to tune. You can see that if you look at the column A and versus column B, these are both random vectors. If you look at the expectation of AI and BI, and the covariance matrix of AI and BI, okay? This is the first moment, and this is the second moment. By choosing mu0, mu1, mu2 correctly, you can see that the first two moments of the A and B are matching. Okay, so this is under generic condition on the random mapping F. So this is exactly the universality phenomena that I mentioned at the beginning of the talk. Many large systems are asymptotically equivalent, despite the differences in microscopic details. So you can see A and B are indeed constructed fairly differently. But what we have done is to match their first two moments. If you match the first two moments, then their testing and training error are asymptotically equivalent. So this is indeed a special case of universality. And we can also make it formal. We can, so again, for this talk, we don't need to go to the details. So there are a few technical assumptions that we have to make, and the detail can be found in our paper. So what we can show is the following. So again, we have the two systems A and B, right? And we want to show the training error of A is equal to training error of B. The way we precisely formalize the equivalence is the following. We say that for any constant C, for any precision quantity epsilon, the probability that A deviates from C by an amount larger than 2 epsilon is bounded by the probability that B version deviates from the same constant C by an amount epsilon, plus some additional term that goes to 0 as P goes to infinity. Okay, and you also have the symmetric version, so you can interchange the row of A and B. So taking these two inequalities together, what we are saying is essentially the following. If you can show the A version converges in probability to a constant C, that happens if and only if the B version converges in probability to the same quantity C. Okay, and similar results also happen for the test error. Okay, so this is something that that formalizes the universality phenomena for the case of random feature model. So I think I just use this very last slide to briefly tell you what is the proof idea. So it's the idea, the high level idea is very simple. So you want to show that the two systems are equal, and the system A consists of a collection of vectors, n vectors, A1 to AN. The system B consists of a collection of vectors, B1 to Bn. What you want to do is to create, so you want to show A is somehow equal to B. What you want to do is to create a smooth bridge or transition from A to B. So you don't want to go from A to B in one step. You want to take a series of tiny steps. So what you do is you first study a system where you replace A1 by B1, but you keep A2 to AN intact. Okay, so the original system and the new system only differ in one entry, A1 to B1. All right. Then next you replace A2 by B2, A3 by B3, so that every two consecutive steps, they only differ in terms of one vector, AI and BI. You can easily see that if you do this kind of a modification, n steps, you can go from A to B. Now, so number of swaps is equal to n. If you want to show, if you can show that each individual consecutive step only incurs a difference of size little o of 1 over n. Why do we need little of 1 over n? Because we have a total of n swaps. Then by doing a telescoping sum, you can show that the difference between A and B in n swaps is of a difference of little over 1, right? This is, of course, known as the Lindbergh approach. And then we also have some additional technical challenges that we have to overcome in this paper. Again, you're welcome to go through our paper for all the technical details. So I want to summarize my talk. In this talk, it's about exploring high-dimensional phenomena, we can call it blessing dimensionality, and these are concentration, asymptotic methods, phase transition, fundamental limits, and universality. So we have shown two concrete settings. One is the spectral methods for non-convex optimization, and the other one is the learning by random features, where we exploited universality and the equivalence theorem. Okay. So last, I want to say that thanks for your attention, and if you are very strong in mathematics, in particular probability theory, and you're interested in doing theoretical research, you're welcome to reach out to me. We're always looking for talents. All right. Thank you for your attention.
Thank you so much, sir, for the talk. So now we can open the floor for questions. So if anyone has any questions, you can unmute yourself and ask, sir, right now.
Professor Ru, thank you very much for your talk. I am Swan, and I had a question on slide number 11. This is very interesting topic. I'm listening this type of connections for the first time. Thank you for this.
Okay, slide 11. This one, right?
Yeah. So here you said you fill matrix A with first 4 million digits of pi, and you see the exactly same concentration of eigenvalues in both the cases. But they really are not deterministic entries if you see, right? Like you can use the decimal entries in pi to generate random numbers, right? If you plot those 4 million entries, I guess you will see the uniform discrete density. Like all the numbers.
There's a certain point I missed. So what do you mean by fractal digits? So you just have each entry is an integer between 0 and 9. So you have 1 of 10 digits. You put it there.
Yeah. So if I remember correctly, at least for first 40,000, 50,000 digits of pi, like 0, 1, 2 up to 9, if you plot the histogram, how many times 0 appears, 1 appears, they roughly appear equal number of times. And in fact, you can use these digits to generate uniform random integers between 0 to 9, I guess. So is it really deterministic? I think those entries are not really
No,
deterministic.
first, okay, I see. So first, it's a good question. So first of all, pi is indeed deterministic, right? Because you can start to calculate the 4 millionth entry of pi, and I can compute it. We'll get the same result if both of us did the correct calculation, right? So in this sense, they are indeed deterministic, right? They are just essentially every time you do it, it's the same thing. It's not like every time you do it, you can get it.
Correct.
But you are indeed correct. No matter how you look at the pi, for example, you look at the histogram. Okay, what is the frequency of appearing digits? 3. It's always around 1/10. If you look at the correlation, so in a sense, this sequence of digits of pi are indeed looking like random, but they are indeed deterministic. So this is a very unique feature. So it won't work. For example, if you have a square root of 2, digits of square root of 2 won't work because then you have a non sort of random, but it's not random. It's also deterministic, right? But it's still it's an open problem, right? You know, why pi? Of course, I want to mention that I skipped the detail. If you just do digits of pi, you won't get this picture. What you need to do is you also need to subtract the mean so that the matrix has 0 mean. You also need to scale it so that variance is equal to 1. So but you get this. After subtracting the mean, rescale it, you get the pi.
So I guess if I did get what you are talking to some extent, the key is to be able to come up with such an equivalent problem. That I think seems to be the most challenging task. Like here, you could come up with 4 million digits of pi. This is the deterministic entries, which is easy to do. And then you know that these two problems, the problem on the top and bottom, they are equivalent. And then you will study only the digits of pi. So that equivalence is okay, but coming up with such an equivalent problem probably seems to be the most challenging task in this type of problems that you're solving. Is that right?
Yeah. So you're right. In some sense, there have been. By the way, this digits of pi. This is open. People have not proved.
Yeah, that's right.
The first one was proved, but the first one, second, but in some sense, we have some intuition why certain things are equivalent. For example, if you look at this case, right, this is the system that we want to estimate. And it's nothing like the Gaussian, right? So that's why Gaussian won't work. But you can show that this system this matrix, tall matrix, has orthogonal columns. Has orthogonal columns. And then what we do next in the universality is really just say this is the CDP is the matrix that I was referring to, but unitary is just a random orthogonal column, random orthogonal matrix. So Gaussian is not orthogonal, but if you orthogonalize the Gaussian matrix, then you can see the match. So we have some intuition. So one intuition is that if you're dealing with matrix, if the singular vectors are generic, then you keep the eigenvalues, a singular value intact, but you replace the singular vectors by random singular vectors. In many cases, you have universality. But indeed, it's very challenging to for some unknown cases, to come up with to guess what is the universality equivalent model, and also it is equally important to find out counterexamples. So can we construct things that are for example, you have the same singular vectors, but you replace same singular value, you replace singular vector, but they are not universal. So it's also very important, instructive to have these counterexamples.
Okay. Okay. Thank you very much, Professor, for clearing.
Sure.
Thank you, sir. So if anyone has any other questions, you can unmute yourself. Okay, so seeing that there are no other questions, I would like to thank Dr. Lu for taking out his time and providing a wonderful lecture on this topic. I'm sure all the participants enjoyed it and found it very informative. So with that, we would like to conclude the session. And for all the participants, I would request to provide the attendance on the attendance link which has been shared in the Google Meet chat. And with that, we can conclude. Thank you so much, sir, for the lecture, and thank you so much to all for attending.
All right. Thank you very much. Bye-bye.